Okay, we're recording. Okay. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, January 22, 2021. I'm your host, Dr. Bill Waller, an astronomer, science educator, and communicator, coming to you on a pretty nice winter's evening in Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our human relations with Earth's life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel, and for this astronomically themed report, as part of the Galactic Inquirer, an online journal that covers diverse astronomical topics. Today, I am delighted to be hosting Dr. Joel Parker, a space mission scientist who will be sharing with us, quote, an astronomer's voyage into space, recollections and reflections, unquote. Joel comes to us from Boulder, Colorado, where he has been working as an astronomer at the Southwest Research Institute since 1996. Before then, he and I both worked at NASA's Goddard Space Flight Center in Greenbelt, Maryland, as members of the Ultraviolet Imaging Telescope team. This particular mission had astronauts operating a suite of ultraviolet telescopes from the cargo bay of the Space Shuttle Endeavour. Exciting times indeed. Since then, Joel has played important scientific roles on a myriad of amazing robotic missions to Comet 67P, Churyumov-Gerasimenko, the dwarf planet Pluto, and Arrokoth, a remote member of the icy Kuiper Belt at the outskirts of our solar system. Next up for Joel is Lucy, an ambitious mission to a passel of asteroids. So without further ado, I want to extend my sincere thanks to you, Joel, for talking with us this evening.
Thank you very much, Bill. And I like the term myriad of missions. That's very good. And you did a good job of saying Churyumov-Gerasimenko. So good job for that.
Thank you.
So thanks for inviting me to give a presentation here of kind of a reflection, as you say, of what I have been doing the past many years. And maybe I'll dive in here and just start sharing some slides.
I'm so sleepy, that's why.
Okay, let's see here. Can people see my screen?
Yes.
Yes.
All right. So, yes, I like to say I'm on a mission, which is very descriptive. I count myself as being extremely lucky in being involved in not one or two, but several once in a lifetime missions. This wasn't by design. It was somewhat of a random walk. When I was a kid, I didn't expect that I would be involved in missions, although I wanted to be an astronaut. But I never really started off thinking, yes, I'm going to be on missions that visit these places in the distant solar system. So I'm just going to back up a little bit and talk about that kid and how he got to where he is now. So here's a nice little family photo taken way back when. If you look at the smallest one in the group, we zoom in on him there, that's me with actually a telescope. So this was definitely foreshadowing of what might be coming in the future. Notice I'm not quite looking up at the stars, but I'm at least getting the idea of a telescope. I was never one of the kids. I never, as a teenager or anything, was someone who built my own telescopes, ground my own lenses and stuff like that. But I always liked math. I liked science. I liked puzzles. All those things kind of melded together and kind of randomly led me in the direction of doing physics and ultimately astronomy. So in graduate school, I studied astronomy. I went to undergrad in physics and astronomy at Berkeley, and then graduate school at the University of Colorado here in Boulder. And I was a ground-based astronomer. So I did kind of the stuff that most people stereotypically think of when they think of astronomers, going to mountaintops, big telescopes and looking at stuff. The picture that you see there of me on the left is me actually standing in a telescope. So this is a telescope at McDonald Observatory. And I'm actually, I don't know if you can see my mouse moving around here, but I'm standing in the tube of this telescope that was built like a tank. And you can see the mirror in the background here. And if very good eyes, a good screen, you could see some flaws in the mirror in the background that look like little holes in the mirror. Those are actually bullet holes in the mirror. There's a whole story about how a telescope in Texas got bullet holes in the mirror. And then the picture on the right is me at the observatory down in Chile at Cerro Tololo, and I'm actually sitting in the cage that hangs off the back of the telescope with a spectrometer back there. So there's this, I have this series of photos, I guess, of me standing in telescopes. But these are, big telescopes with mirrors up to 4 meters in size, doing very classical astronomy. The things I studied at the time were called the Magellanic Clouds. These are galaxies that are neighbors of our Milky Way galaxy. There's the small Magellanic Cloud and the large Magellanic Cloud. These are visible from the southern hemisphere. That's why I went down to Chile for observing. And I actually did my thesis work on one area in this large Magellanic Cloud called 30 Doradus, which is basically a star-forming factory of huge, massive stars that are, tens of times the mass of our sun. So I was really doing classical stellar astronomy for many years. The downside of ground-based astronomy is the Earth happens to have weather. And although weather can be good for many things, it's not necessarily good for astronomy when the weather is lightning and raining. This is a picture of Kitt Peak. Beautiful picture, but not beautiful if you're an astronomer. So one way to avoid the trials and travails of weather on Earth is to get above it all. And one way to get above it all is go to space. This is a picture of the Hubble Space Telescope in orbit around the Earth. And so I started getting involved in space telescopes, Hubble being one, another called the International Ultraviolet Observatory, and a number of others. So these telescopes, both being able to get above the atmosphere for weather, also are able to look in wavelengths that we can't see from the ground, like ultraviolet light, or some parts at longer infrared wavelengths where the water in the atmosphere blocks it out. So I did a lot of work with observations and projects on the Hubble Space Telescope, which I continue to do. Hubble just had its 30th anniversary, I believe, of flight. Amazing. And it's still creating amazing data. So I then moved on to doing other telescopes in space, like Bill mentioned. I got involved after graduate school. I went to Goddard Space Flight Center and got involved with a project called the Ultraviolet Imaging Telescope, UIT, which flew on 2 shuttle missions. I wasn't involved for the first one, but I was involved in the second one. And this is, as Bill mentioned, there was a suite of telescopes, UIT being one of them, that flew in the payload of the space shuttle. And there's this beautiful picture from the UIT mission that I love that shows the telescopes here in the payload bay of the shuttle. And those of you familiar with the sky, you'll see Orion in the background here. You can see the belt stars and the sword stars and nebula. And I love this picture. I wish I was on the shuttle to be the one to have taken the picture. Bill and I spent, I think, most of our time in a basement in Huntsville, Alabama. But it really was an incredibly fun mission to be working with the space shuttle with telescopes and actually pointing the telescopes by having them move the shuttle as well as this pointing platform to point at things. So that was just an incredibly exciting adventure. I looked at massive stars when I was involved with that, but then I started working on objects closer by in our solar system, like stars or like comets, for instance, Comet Hale-Bopp. And I got involved in yet a different mission that also used the space shuttle. When I moved back to Boulder and worked for the Southwest Research Institute, a fellow named Alan Stern was involved in a lot of ultraviolet work and space mission work. And I got involved with him with this small telescope that flew on the middeck of the space shuttle and observed things like Comet Hale-Bopp. And the picture in the background is in the visible. This picture with the red insert is an ultraviolet image taken with our camera that flew on the shuttle of the comet. And looking in the ultraviolet just gives you different and more information about the objects you're looking at. This is actually a picture here of the telescope. It's a small telescope that was looking out a port window of the shuttle. So this just shows the telescope here with a little camera sitting on the back. And the astronauts just, after launch, they attached it and once again would point it by pointing the shuttle where we wanted to go. So here's a picture of the shuttle set up for launch. And right on the side of the shuttle here is this little UV transmissive window that we hooked our telescope up into. So it was really phenomenal to be able to work with telescopes that flew on the shuttle. Now, pardon me, I'm going to step back a little bit here because I'm going to talk about comets and things called Kuiper Belt objects. And I just want to give some context for that. So in the whole scenario for how the solar system forms, we start with basically a cloud of gas and dust that slowly collapses. And as it collapses, it forms a disk. And that disk over time breaks up into regions that form planets. And ultimately, you have a solar system with a sun in the middle and planets orbiting around it. In our solar system, we have the planets that we're all familiar with that basically divide up into 2 zones. One zone is the terrestrial zone, which has the rocky planets, Mercury, Venus, Earth, and Mars. And then the outer zone, which has the giant planets, Jupiter, Saturn, Uranus, Neptune. And so that makes up the bulk of the solar system. There's a lot of reasons why we have rocky ones on the inside and big gas giants on the outside. But I missed one object out there that some of you may have heard about, this little thing called Pluto. Pluto doesn't fit this two-zone idea of terrestrial inner zone and gas giant outer zone. So what about Pluto? Why is it this misfit out there on the cold outer reaches of the solar system? So in 1992, we discovered the third zone of the solar system called the Kuiper Belt. All these years since Pluto was discovered, and in fact, we just passed the anniversary of, or we're just coming up on the anniversary of Pluto, which was on February 18th, 1930. All those years, Pluto was giving us a hint that there was more out there. It was, in fact, not a misfit. It was telling us that there's more like it out there. This Kuiper Belt is this zone beyond Neptune's orbit that has all this leftover debris from the formation of the solar system. And it's all the small objects, Pluto size and smaller. That is the pieces of icy rock and rocky ice that never really got together to form planets. And it's the source of some of the comets that we see, called Jupiter family comets. So Pluto is no longer a misfit. In fact, it is the king of the Kuiper Belt. Other Kuiper Belt objects started being discovered in 1992, and now we know hundreds and hundreds of these Kuiper Belt objects. So we now have this third zone, previously unknown, of the solar system. Beyond that, we have something called the Oort cloud. These are objects that are like those icy, rocky leftovers from solar system formation that got kicked out due to interactions mostly with Jupiter. Jupiter is kind of the big bully of the solar system. Any little bit of debris that gets close to Jupiter either gets hit by Jupiter, gets flung into the sun, or kicked out into the far reaches of the solar system. So you can see this little inset here of the Kuiper Belt. It's a little teeny dot inside this much larger structure of what we call the Oort cloud. And the Oort cloud is at a much greater distance from the sun, 5,000 to 50,000 times the distance of the Earth to the sun. And this has also been the source of what we call long period or Halley family comets that come from all directions. So this is kind of the structure we have now of the solar system, with the three zones: the inner rocky zone, the outer gas zone, and the Kuiper Belt, and then the Oort cloud. And that kind of gives you an idea of what the Kuiper Belt objects and the comets come from. And let me just finish up talking about comets here, just to remind you, what is a comet? When we talk about comets, the parts of a comet really is driven by this thing, the nucleus. This is the central engine of the comet. It's one of those little teeny bits of leftover icy rock or rocky ice. And this is a small, usually a few kilometers, few miles in diameter, that's buried inside this larger thing we see as a comet with this beautiful tail. That tail is a combination of a dust tail. We see it because that dust is reflecting sunlight and the solar wind is pushing the dust back. And in fact, the solar wind was hypothesized to exist before we could actually measure it, because of how comet tails always appeared to be pushed by some invisible force from the direction of the sun. Also is the ion tail, which is the gas that is blowing off and glowing from the sun. So this is pointing away from the sun all the time. The dust tail is a combination of the path that the comet has takes plus the push from the solar wind. So all of that makes this comet that is then buried in this huge coma of gas and dust, which could go out for millions of kilometers. And in fact, the comas of comets can actually be the largest structure in a solar system, larger than the sun in size in a couple cases. Very, very tenuous, very hard to detect. And comets, of course, are just beautiful. I mean, here I'm just going to go through some just beautiful pictures of comets, seeing what the coma look like, what the tails look like, all the structure that you see. And this is one of my favorite comet pictures. It's Comet Lovejoy setting behind the Earth as seen from the International Space Station. So you can see the comet here just along the limb of the Earth. I just love this. It's a gorgeous picture. But besides being beautiful, comets are scientifically interesting. They're relatively pristine materials left over from the formation of the solar system. So studying them can tell us a lot about the history of the solar system 4 billion years ago when it formed. They're kind of these escaped examples from those more distant regions of the solar system, the Kuiper Belt and the Oort clouds. So they're a little bit easier to study because they come in close sometimes. Now, occasionally impacts might be kind of a concern. The dinosaurs know this as well as anyone. When these objects hit the Earth, catastrophe can ensue. However, the impacts have a silver lining because they can deliver water and organic material into the solar system, into Earth. So Earth is bombarded by hundreds of tons of material every day from comets and asteroids. Usually it's just little bits of dust and we're never aware of it. Sometimes you see it as shooting stars. Sometimes they actually make it to the ground. And these bring all those important organic molecules, metals, silicates, and water. And just to show an example here, I love this picture. This shows the Earth, and that little blue ball you see is all the water of the Earth on the surface of the Earth gathered up into a ball over the United States, to just give you an idea of how little water there is relative to the whole size of the Earth. And a lot of this is supplied by asteroids and comets. And in fact, for every cup of water that you drink, there is comet water in that cup. So every day you drink your water, you're drinking comets. And Earth isn't unique. Here is Europa, one of Jupiter's moons, and the water that you see that we believe is there. So water is all around the solar system, a lot of it coming from comets. So now let me talk a little more about some of the missions I worked on. So all of that preview was about comets. One mission I got involved with here at Southwest Research Institute was called Rosetta. Because of the work I did working on comets and working in the UV, we had a camera that we proposed for and got put on this mission that was run by the European Space Agency with some partnership with NASA called Rosetta, that actually went out to land on a comet. Some people are still surprised. In fact, I'd say most people are still surprised to hear that we actually have landed a lander on a comet. So this shows the Rosetta spacecraft, artist conception, and the lander. And this is a really big spacecraft. So the tip-to-tip wings of the solar panels here, 32 meters. So it's about 100 feet tip to tip when the wings are folded out. The spacecraft itself is a cube. It's kind of like a Borg spaceship, for those of you who know what Borg are. About 2 meters cube in length, in size. And then the little lander Philae is about 1 meter cube. It's about the size of a washing machine. So that was the Rosetta spacecraft and mission. This is a mission that launched in 2004 and flew 10 years to get to the comet Churyumov-Gerasimenko, comet CG for short. And this is a Jupiter family comet. It's about 4 kilometers in diameter. Until the Rosetta mission launched, so it launched in 2004, it got to comet CG in 2014. This was our best guess at what the comet looked like. Because remember, the nucleus of a comet is so small, we cannot actually see the nucleus even with our best telescopes because it's so small and shrouded by gas and dust, usually by the time we see it. So using various tricks from the Hubble Space Telescope, this was our best guess at what we thought the comet would look like before we got there. So this is what we expected to see. This is what we got. Looks a little bit different than our best guess. And this really shows how important it is to actually go and study in place, in situ, the things in the solar system up close and personal, because there's so much more you can learn about the details, about the shape, about what the history is. And look at this, it's what we call a contact binary or bilobe. It looks like 2 pieces that got stuck together. And in fact, this shape made us start calling it the rubber duck because it had this shape. So it made it easy. We would talk about the head of the comet, the body of the comet, the left wing, the right wing. So comet Churyumov-Gerasimenko ended up being called the rubber ducky in a lot of our science team conversations. And it's a crazy place to send a spacecraft, because think about it, you build a spacecraft in a clean room, and then you send it to one of the dirtiest places in the solar system that's spewing off gas and dust and things like that. But it was a fantastic mission. It ran for 2 years and ended in 2016, and we're still studying the data. I also got involved in the New Horizons mission, which flew another one of these small ultraviolet telescopes that I was involved with. It's called ALICE. It's an ultraviolet spectrometer. And so we took basically the same spectrometer, same camera that we put on Rosetta, and we put it on New Horizons. This spacecraft, which is about the size of a grand piano. And this spacecraft flew out to Pluto. So this launched in 2006. It also took about 10 years to get to its target. So these missions are a practice in delayed gratification. So here's another example. This is the best image we had of Pluto, in this case from the Hubble Space Telescope, before New Horizons. So this is what we expected. And when we got there, this is what we got. So I think many of you have probably seen this, the image of Pluto, this part here called what we're called the heart of Pluto, which is a vast plain of a nitrogen glacier on Pluto. Pluto was incredibly geologically active, something we didn't expect. It has mountains of frozen water ice as the bedrock, nitrogen glaciers, methane capped mountains, incredibly complex, diverse geology and terrain that is still active for something so small, so far out in the cold reaches of the solar system, that is still being a puzzle for us to solve on how that is. This is a nice kind of color enhanced image of Pluto, accentuating the different types of terrain and its moon Charon. It really is a binary planet system because Charon is about half the size of Pluto. And when they orbit each other, the center point of their orbits is actually outside of the body of Pluto, so that they're orbiting around a central point that's between them. So Pluto, again, imagine working on a mission for 5 years to build the mission, years before that to write the proposal and plan for the mission, 5 years to build it, 10 years to fly it, and then you get there, this is what you see, and you now have a lifetime of data to study. It's an amazing journey, but it really takes a lot of patience and detailed planning. But then you get images like this. This is Pluto. And, there's a whole question about whether Pluto is a planet or not, whatever you call it. Whatever you want to name it, Pluto is clearly a world. This is a picture taken as we are flying past Pluto. You can see haze in the atmosphere with layers. You can see mountains casting shadows right around the terminator where it goes from day into night. You can see this huge plain of nitrogen glacier. I mean, if you were in Star Trek and you were orbiting this object and getting ready to beam down, you would say, beam down to the planet, Scotty. You wouldn't say, beam down to the Kuiper Belt object or the dwarf planet or whatever you want. So whatever you call it, it is a beautiful object to study in its own right. And then after Pluto, we had one more object that we were able to fly by in 2019 that is much, much, much smaller. This is now only about 30 kilometers end to end. It was called Ultima Thule, but its official name is Arrokoth. And think about this. This also looks like a double object, just like Comet Churyumov-Gerasimenko look like two pieces that stuck together. So does this. And that is telling us something about the formation of objects in the outer solar system. And there are a lot of models that are starting to incorporate how you get these contact binaries. So I'm going to talk about one more mission here that I got involved in. Basically, once you get involved in one mission, as long as you do a good job and things go well, there's always a new mission coming up that you may be able to use your skills for. In this case, this mission I'm working on now, I'm still working on New Horizons, but the mission that is now taking most of my time is this mission called Lucy. And Lucy is going to fly out to the orbit of Jupiter to study some small bodies out there that are called Trojan asteroids. And you note that our little icon here for the Lucy mission is the Lucy fossil. And the reason for that is in the same way that the Lucy fossil was able to tell us things about the origin of our species and the evolution, going to these Trojan asteroids is going to be able to tell us something about the origin of the solar system and its evolution. So here's a little movie showing our solar system looking down from above, Earth in the middle, with Mercury zipping around, Venus, Earth, Mars. And then out in the distance, you have Jupiter way out here. And then you have these clouds of these Trojan asteroids at what are called Lagrange points. They're kind of stable orbits out there leading and trailing Jupiter, the L4 or Lagrange 4 and Lagrange 5 points. These areas are stable points in the solar system where the objects that were captured there 4 billion years ago are still there. That's why we talk about these as fossils and relics. And the spacecraft is going to go out there to study these Trojan asteroids. And it's a very interesting, complex orbit. So it will launch this year, October 2021. It's going to take a few orbits around Earth. It's going to fly by an asteroid on its way out called Donald Johanson, the discoverer of Lucy. And no, that's not a coincidence. The asteroid didn't have an official name. So since we knew we were going to fly by it, we actually gave it a name. We fly by that in 2025. We get into the L4 swarm of Trojans where we fly by 4 objects. We will fly by Polymele, Euripides, Lucas, and Orus in this cloud of Trojans. And all of that will happen in the year 2027. We come back into the inner solar system for a little loop around, and then we go out to the L5 cloud, where we're going to fly by a binary pair of these Trojan asteroids called Patroclus and Menatius. And that will happen in 2033. So again, we're talking from launch, a 12-year mission, 11 to 12 years. And if everything's going well, we get an extended mission, we can do these loops again for years and years and continue to visit Trojans in the clouds. And what I'm doing in the Lucy mission is I am building the Science Operations Center. And when I say that, I'm the manager and director of the Science Operations Center. And I just make sure that the money and the schedule is such that the people who actually get to do all the building make it happen. The Science Operations Center is involved in planning the science sequences that we're going to do when we fly by these objects. And we process the data when we get them and create the pictures and all the data that we then use to study the objects. And also we archive the data so people around the world can get the data for free to do their own studying if they want. So building a Science Operations Center, I'm not going to go into these details, but it's less glamorous than maybe it sounds. You have to design requirements on the planning, the commanding, the data processing, how you do your operations. You do a lot of documents. We have documents that are taller than the spacecraft. The spacecraft, is several meters tall. You have many, many, many more documents just to make sure your operations and management, security, interfaces, everything is working correctly. You have all the hardware for Science Operations Center, the servers, the number crunchers, the network. You have all the software that you have to build for building the command loads and processing the data. You have lots of reviews. Everything gets reviewed multiple times. Lots of testing. We have a saying in the mission business, test as you fly and fly as you test. Meaning, however you do your test, you want to make it as close as possible to how you're going to do things in flight. And then when you fly, you want to do things as close as possible to how you tested. And then finally, after all that's done, you actually get to fly. You get to launch, and then you wait several years till you actually get to your target. So when you build a Science Operations Center, this is how a lot of people picture a science or mission operations center. A mission operations center actually sends commands to the spacecraft. and manages the spacecraft. Science Operations Center manages all the instruments. So a lot of people have this vision of a Science Operations Center, a big room with monitors and consoles. It's not really that anymore. This is our Science Operations Center. It's a rack. It's a rack of a lot of computers, and we all log in remotely to do our work from the office, or as for the last several months, from home. So I have had the amazing experience working on another mission for the Lunar Reconnaissance Orbiter of sitting in my living room, eating breakfast and watching data come down to my laptop live from the moon. That's pretty amazing. I always say when that, it's like we are living in the future. The center is this rack of computers, but it's also the people who do the programming, the planning, the command sequencing, the testing, the data processing, the archiving, checking, everything. It's really the people doing all that work. The computers just help us do the work we want to do. And then there's the mission team beyond the science operations team. These are the scientists, the engineers, all the other programmers who access the SOC to get the data from their offices or home. So we're still in the process of building the Science Operations Center to be ready for launch in October. And I just want to finish up with just saying, maybe this interests you. Maybe some of you think, hey, it'd be fun to work on a space mission. How do you work on a space mission? Well, there's around, for New Horizons, there's about 2,500 people who worked on some part of New Horizons over 15 years. Rosetta was about the same. It can be, like I said, a very long-term commitment with delayed gratification. Your time is not your own because things have to get done and launch at a certain time, and the orbits of the planets aren't going to wait for you. You have to look at the day-to-day details, but you have to take the long-term view. So if that's for you, what is the right stuff to work on the space mission? Well, a lot of people think, yeah, it's true. Astronomy, physics, math, geology, atmospheric science, biology, chemistry, all types of engineering, robotics, programming, and image processing. Any of those backgrounds are absolutely applicable to doing space studies and working on missions. But there are many other avenues to get to work on space mission. People who never imagined they would work on a space mission based on what they were interested in or went to school for. That includes educators, communicators and journalists, accountants, project managers, planners, quality assurance specialists, people doing administration, graphic designers, and other kind of artists like modelers and drafters. There are so many different paths that you can take to get involved in space missions. If it's something you really want to do, there is probably a place for you. And students, even if you don't have a degree yet, even if you're still going to school, we've had high school students and college students involved. And in fact, I just want to mention the New Horizons mission actually has an instrument called the Student Dust Counter. This instrument was completely designed, built, run, operated in flight by college students. So there is a lot of opportunity to do that. So I just want to close with a couple of my favorite images. So this one is beautiful. This simple blue ring. This is actually the eclipse of the sun by Pluto. the only way this picture can be taken is being past Pluto. This is really a beautiful image because it shows you we went beyond Pluto. And it shows the atmosphere, and it shows a lot of detail on the limb if you look up close. And then I think probably my all-time favorite picture from a mission is this. This is a selfie, a space selfie of the Rosetta spacecraft with the comet Churyumov-Gerasimenko hanging in the sky. Just almost, it almost looks like you could touch it. It's actually several kilometers away. But it is a picture of an object that we built visiting an object that is an ambassador from the formation of the solar system 4.5 billion years ago. And this picture, when it came down, this was the one that really for the first time made me feel like I was there. That this is something I knew, that I touched, that is out there visiting a comet. And it's moments like this that all the work, all the years of school, all the preparation lead up to that. Even though you learned so many amazing things about ourselves and the formation of the solar system, it's these moments where you can almost touch what you've done that really just bring it home to me. So I think with that, that is the end of my slides. And I would love to take any questions.
That was super, stellar, in fact. And I wish you so much luck with Lucy in the sky with diamonds.
And I have to say, I had to ask the engineers, is there in fact anything of diamond on the Lucy spacecraft? And there is.
There is.
There's a beam splitter on one of the instruments that's diamond. So we can officially say that we do have Lucy in the sky with diamond.
That's awesome. So I have some questions from the chat.
Great.
And you pretty much answered this, but you could certainly elaborate. It's from Paul McGeary. The comet and the Kuiper Belt object Ultima Thule both have two lobes. Is there evidence that this is a common structure for Kuiper Belt objects?
Yes. And I just want to say Ultima Thule was kind of our placeholder name for that object. It's very fitting. Ultima Thule means beyond the known world, off the map, basically. And this object that we had nicknamed Ultima Thule at the time was 1 billion miles further from Pluto. So Pluto is 3 billion miles from Earth. This was another 1 billion miles. And the official name for Ultima Thule is Arakoth, which means the sky in the native language of the first peoples in the Maryland area. That was chosen because the Mission Operations Center was at the APL that's based in Maryland. So anyway, with that whole prelude there, the bilobed structure, the contact binary, the fact that we've seen 2 of them, and actually there are other objects that we have seen. These aren't the first or only objects we've seen that are bilobed in small bodies. It definitely tells us something about the dynamics of where these objects formed, because to get something to come together and stick rather than collide and break apart tells you they had to be moving rather slowly, like meter per second, like walking speed, or they would have basically disrupted each other or some other type of non-bilobed ending. So it does tell us about how many objects had to be out there and how fast they had to be moving relative to each other. And so that does constrain some models about the formation of the solar system. So these are being used to either support or throw out some models of solar system formation.
Okay, I have another question. It's more of a comment and it's more philosophical. It's from Eleanor. It says, scientific results take time. We aren't great at delaying gratification. And then she's not finished. So what is the status of international collaboration given this delayed
Sure.
gratification? And how much is funding impacted by the fact that scientific results take time?
So I do think Rosetta was a really great example of that. There are many other international collaborations, not just in space astronomy, but other areas of science as well, and in the arts. But Rosetta, it was my first really tightly integrated international project, and it worked really well. You know, every big project really revolves around how it's organized, how it's managed, how the communication is handled. And there are silly things you have to think about, like, okay, Rosetta is run by the European Space Agency based in Europe, but it has partners throughout the US. When do you hold your teleconferences? And we've had projects that include, Asian partners, European partners, American partners. Just the simple logistics of when you set up telecoms and keeping track of time zones requires, an engineering degree, and is harder than rocket science sometimes. But as long as the groundwork is clear to everyone works within that structure, because it's not a goal that is driven by national boundaries, at least on the science level. On a prestige level, it is, absolutely, certainly. But scientists, and this is one reason I got involved in astronomy, it's an international subject. And I got to meet astronomers around the world who wrote the papers, and that continued in missions. We all had this goal of making the mission work. We all wanted our instrument, of course, to get all the data we wanted to get. And sometimes you had to negotiate, okay, I want to point this way, that camera wants to point that way. We'll split the time, and not everyone gets what they want, but everyone gets something. It's the same negotiations. At the science team level, it's just a team. And I really appreciate that. And we all know it's going to take time. We know what we sign up for. I should mention, many of us on a personal level sign up for some of these missions, even knowing we may not be working or even alive at the time the mission reaches its target. And I think that's an incredibly valuable, multi-generational view that I think personally is important, and I'm really pleased to see that. I'm even not just, whether you're going to be alive or not, but handing off generationally to the younger scientists who are going to be the ones who are going to take the mission to its finale.
Mhm. So I have one comment from Cindy. Thank you so much. I can't believe I understood everything you said. Tra-la.
Well, thank you for that. That is really kind. I'm glad that I hit that mark.
So we have time for a few more questions. If anybody wants to just unmute and ask their question, feel free to go ahead. There we go.
I have a question.
Sure.
Go ahead.
I want to make sure that the students heard your comment about what made all the schooling and hard work worthwhile. I want to make if you could state that again.
There are so many ways to say that, but part of what I got into in astronomy and physics was just enjoyment of what it was. And like I said, I liked math, I liked puzzles. I was amazed that you could work at a job where the job is making up a question and then making up how you would answer that question. I mean, how fun is that? You get to invent your own puzzle and then try to solve it. It does take patience. It does take focus and attention to detail. You're working as a team very often in these large projects. So you have people watching your backs. And, you know, even in smaller groups, Bill and I have collaborated on projects, just he and I working together or with a small team of people studying data from the Hubble Space Telescope or on other projects. There's a lot of interactions. So there's everything you know that you've spent your time learning about in training, whether it's how to program in Python or doing the math or, you know, doing really good modeling or design or communication. And going into a project that you know is going to be for the long haul. And if that is the type of thing that attracts you, it's absolutely worth it. And I find it so much fun in the day-to-day, to be honest, that those 10 years go by very quick. In fact, sometimes they sneak up on you. Suddenly you're almost at the target going, oh my gosh, I meant to have that code written and it's not done yet. You know, you had 10 years to do it, but you were doing so many other things.
Any other questions? All right. Well, I just want to end with a final compliment from Richard Lukey. Dick, this was super. Thanks, Joel. Thanks, Bill. So I want to thank you all for being a part of this. And I promise to get the recording up on Doc Waller's Earth and Space Reports, and also with my colleague, Mike Deneen, it'll get up into the Galactic Inquirer. What a treat,
Awesome.
Joel. So thank you so much. Yes, curious minds want to know.
Thank you, Bill, and thank you everyone who joined us. That was fun.
All right. Well, go well, you guys. Take care.
Bye, everyone.
Thank you. Thank you very much.